Okay, so the colors are important. So let's get back to the same question. So if they were wearing something dark, outside temperature is going to be 120, inside temperature is 98.6, so they will heat up faster. They think that they're going to feel cooler, so the question is why? All right, so we didn't really answer the question. So what do we know about heat? So it's a form of energy that flows from hot to cold. So if there's a temperature difference between two regions, there's going to be heat flow. So if there's a temperature gradient is going to cause a heat flow. All right, so mathematically, we got the definition of it. So it's going to be energy in transit from hot to cold. So if there's a temperature difference, there's going to be heat flow from hot to cold. That's it. We can express the temperature difference usually in calculations in terms of Celsius, Kelvin, and sometimes Fahrenheit. It doesn't matter. Also, heat is created through the energy conversion process. Friction is going to turn mechanical energy into heat. So what's happening is through friction, the molecules are vibrating faster. So the motion of the molecules is going to increase the average kinetic energy of the molecules, which means that the surface temperature is going to rise up. So if there's a temperature difference, there's going to be heat flow. So surface is going to be hotter than the room, so which means that heat is going to flow from the surface to the room, increasing the...
When a falling body hits the ground, each bounce is smaller than the last. Why? Because the kinetic energy of the body as a whole becomes transformed into the chaotic motions of the atoms that compose it. And that process is very similar to heat flowing into a cold body, and the end result is the same. All of the available energy eventually becomes shared out as kinetic and potential energy of random motions of all the atoms.
Okay, so this is going to require a little bit of thinking. Okay, so open up chapter number 15, heat. Okay, so let's open up the lecture review. And then let's get up to 27. We have to have a discussion regarding this. We've got to get up to 27 and have a discussion. So which one is more difficult to heat up? A cup of water or a gallon of water? You know the answer, right? So the gallon of water is going to be more difficult to heat up. So if you want to increase the temperature of water, if it's a gallon of water, it's going to require a lot more heat to cause a temperature change, right? So it's going to require a lot more heat. So more massive something is, the more heat is going to require, in essence. All right, so what's the relationship between the amount of mass and the amount of heat needed to heat up that mass? Obviously, the more massive something is, the more heat it's going to require. Okay, that's one of the things. So which one is going to require more energy, more heat? Heating water by 10 degrees or 100 degrees. Once again, it's common sense. So if you want to heat something up by 100 degrees, you have to put more heat into it. So more massive something is, more heat is going to be required. And the larger the temperature difference you want to cause, the hotter you want to make something, the more heat you have to put into it. And then the third thing is the heat capacity. So what is a heat capacity that we have to focus on? All right, now finally we're back in the lecture. Caught up with the lecture. All right, so how do you want to make something, the more heat you need to put into it? That's what it means. So the bigger the temperature difference you want to cause, the more heat is going to be required. More massive something is, more heat is going to be required. How much heat you put into it is also going to depend on the material itself. So C represents something called a specific heat capacity. All right, so that's the one that we will focus on, specific heat capacity. If you're going by the book definition of it, it's the amount of heat required to raise the temperature in this given substance by 1 degree Celsius. All right, so that's the book definition. I'm not going to use the book definition. I'm going to use a definition which is a little bit more intuitive. The specific heat capacity represents the tendency to resist temperature change. Any temperature change. Resistance to temperature change. Or tendency to resist any temperature change, or resistance to temperature change. It's almost like heat inertia that you have. It depends on the material. Some materials will be very resistive to temperature change, and some materials are going to be easy to change their temperatures. All right, so the question is, where does this resistance come from? This becomes an interesting research topic normally. Here's what I'm talking about. So you got 4 different materials. All right, so you got water, aluminum, lead, alcohol, and then we're going to increase the temperature of each and every single material by 100 or by 10 Kelvin. I was going to say degree. Degree is not degree is not something that you can use with Kelvin. Kelvin. It's not degrees of Kelvin or Fahrenheit. So we want to increase the temperature by 10 Kelvin, each materials. Notice that the amount of heat required to cause this amount of temperature change depends on the material. And then when you look at the numbers, you notice that the water is going to offer the most amount of resistance to temperature change. So if you want to change the temperature of water by 10 Kelvin, you have to put in a lot more heat than any other material. So you will notice the same thing when you're looking at specific capacities for different materials. The one that you guys could relate the best is the far right, because we're expressing everything in terms of calories as opposed to joules. Another reason why these numbers are easier to relate to is because the only thing you have to do is look at the one that has the largest heat capacity. It's water. Okay, so the water has the biggest heat capacity. It's 1. Everything else relative to water is going to be smaller. So what that means is the water is going to require the most amount of heat to undergo a temperature change. So water is going to offer the most resistance to temperature change.
The skin is not just an inert coating. It is an active organ with a vital function. Skin keeps the body cool. This heat-sensitive camera shows in red and yellow the hottest areas on a body in action. During heavy exercise, muscles generate enough heat to boil several cups of coffee. This heat would easily damage the internal organs unless the body did something about it. Just below the skin surface are 3 million temperature control units. These are the sweat glands, each a coiled tube 4 feet long, loaded with liquid. As the body heats up, the tube contracts, squeezing a droplet of sweat out onto the skin. As the sweat evaporates, it draws heat from the skin and cools the body. A body working flat out can expel 2 pints of sweat per hour.
Okay, so sweating is human temperature, body temperature, the core temperature. Okay, so this is problem number 1 from the handout. So for this particular person, the body generates this amount of heat. So the question is, if the heat were not removed from the body, how much would the temperature of the body rise? We are working on. So this guy's got a mass. This is the amount of heat that's generated by the body during the process, expressed in terms of joules. So how much would the temperature of the body increase in terms of Celsius and Fahrenheit if there were no sweating? So evidently it's 20 calories of heat is being generated within half an hour. All right, so this is 20 calories of heat is generated. That's nothing. All right, so the specific heat capacity of the body is this number. Okay, so the rest of it is straightforward. So this guy is 145 pounds. All right, so we grab the equation. So this is the equation that we will get to use. This section of the equation we will use. Okay, so solve for delta T. And then the rest is straightforward, just plugging them in. Okay, so we'll get the answer in terms of Celsius and convert it to Fahrenheit. It's a 6 degree Fahrenheit rising to temperature. So, which means that the body temperature would go up to 105 degrees. All right, it's not necessarily deadly, but it could be less than evidently if we did not sweat. So sweating is one way the body regulates heat. Okay, so a couple of things that we know. The freezing makes sense. The melting we understand. All right, and gas can condense into solid, and the solid can turn into gas. That's called subliming. Liquid can evaporate, turn into gas, or it can condense back into liquid. So there is a question here that we will get to talk about. That's the evaporation. Okay, so whatever that means, just hold on to it. Okay, so let's talk about the 3 states of matter as opposed to 5. You got solid, you got liquid, and you got gas, obviously. So solid ice, okay, negative 30 degrees Celsius, so increase it to 0. At 0 degrees, it's going to melt. At 0 degrees, it's going to melt. Increase the temperature at 100 degrees, it's going to turn into steam. Okay, so when you put heat into it, notice that the ice temperature is going to go up. When you get water, when you put heat into it, the water temperature is going to rise up all the way up to 100. And then you can keep increasing the temperature when it turns to vapor after a certain point. But what's happening when you reach the 0 degree? You're putting heat in, There's no change in temperature. It doesn't cause a temperature change to 0 degrees. The amount of heat that you put in is going to go into melting the ice. Okay, so under 0 degree, the amount of heat that you put in is going to warm up ice, which means that the molecules are moving faster. And then over 0 degree, the heat that you put in is going to make the molecules move faster, so the water is going to heat up. When you reach 100 degrees, you put in heat. There's no change in temperature. Instead, what's happening is the water starts to undergo a transition. It gets converted into steam. It's called a phase change. So the phase of water is changing. At 0 degrees, there's a phase change. At 100 degrees, there's a phase change. So during these phase changes, the question is, what happens to the amount of heat that you put into the system? Where does it go? Well, ice turns into water, so which means that the amount of heat that you put in is going to go into changing the internal structure of ice. So it goes from being solid into liquid, which means that the molecules will break apart, and then they will move further apart. Right? And then at 100 degrees, the amount of heat that you put in, this time is going to break up the water molecules, so it's going to turn into steam as a result, and then the molecules will move further apart as well. All right, I'm just thinking, do I care about this one? Okay, let's see calorimeter problem. Is it interesting enough? I'm trying to figure this out. Okay, now let's just do this. So we got a calorimeter cup made up of aluminum. All right, so the mass is given. Contains this amount of water. All right, so this is the mass of water. Okay, so the cup is made up of aluminum. The water and the cup are at the same temperature, so it's 18 degrees Celsius. So that's the initial temperature of the system. And then we place an unknown material, which is initially heated to the temperature of 97 degrees Celsius. And then we put this into the water. Okay, so here's the mass of the unknown material. Here's the initial temperature of the unknown material, 97 degrees. All right, and then you wait for a while until there's a common temperature. All right, so this ends up, there's a temperature difference between water and the unknown. So there's going to be a heat flow until there's a common temperature and equilibrium temperature. So the equilibrium temperature is the final temperature of the system, which happens to be 22 degrees Celsius. Okay, so from that, can we figure out the heat capacity of the unknown material? Okay, normally this would be a lab done at school. Not one of my favorite labs. This lab usually takes about 2 hours, and half the time it doesn't work. And I've seen the instruments at school, at our school, it's like those lab instruments for this one is from 1980s usually. It's a very arduous experiment. All right, so a couple of things. We're trying to figure out the specific heat capacity for the unknown material. All right, so you look up the heat capacity for water, so it's this number, the aluminum is this number, so these are the numbers that we pick up from the tables, and then this is what we're trying to figure out. Okay, so how do we do a problem like that? The only thing you need to know is the conservation of energy, which means that the heat gained and the heat lost is going to be the same. Okay, so the amount of heat gained by the system is going to be the same as the amount of heat lost. Okay, so aluminum and water will gain the heat, right? And the unknown material is going to lose the heat. So whatever the heat that the unknown material loses is going to be gained by the water and the aluminum system. All right, so this is the setup. We will get to use the same formula for both of them. All right, so this is the amount of heat gained by aluminum plus the amount of heat gained by water is going to be the same as this. These numbers will add up to the amount of heat which is going to be lost by the unknown material. Okay, so the temperature changes will not be the same on both sides. Okay, so temperature change here is different from the temperature change there. All right, so this is, I came up with a general setup for that one, so we will have to fill in the blanks. Okay, so this is the final temperature. This is the initial temperature of aluminum. Our final temperature of the system, this is the initial temperature of water. These two will be at the same temperature. This final temperature of the system, this is the initial temperature of the unknown. Okay, so solve for the heat capacity for the unknown. All right, so I'm keeping the algebra straightforward. Okay, algebraically, this is as far as you go. Now I'm putting the numbers in. And when you do that, this is how you figure out the specific heat capacity of the unknown. All right, this was not bad, except there were too many numbers. Okay, the thing to focus on right now is what's happening during the phase change. What's happening during the phase change? Okay, so when you put in the heat, when there's a temperature change, obviously heat is going into the kinetic energy of the molecules, but during the phase change, when you put in heat, there's no change in temperature, which means that heat is not going into the kinetic energy of the molecules. Instead, it's causing the molecular bonds to break. And then you put in more heat, temperature rises up, so it's going into kinetic energy. But once you hit 100 degrees, there's no change in temperature. Instead, there's a phase transition. All right, so during these phase transitions, the amount of heat that you put in goes into the potential energy of the molecules. All right, so this is the amount of heat that you put in per mass, per kilogram of mass, to cause a phase transition. So obviously, it's not going into the kinetic energy of the molecules. Instead, it's going into the potential energy of the molecules. And potential energy of the molecules is related to the relative positioning of the molecules. All right, so when they are, okay, so just trying to get to, and I'm not finding the visual enough. Okay, so in the solid state, the molecules are closely packed together. In the liquid state, they're further apart. Usually you got two molecules attached to each other, they roll over each other. In the gas state, the molecules tend to be freer from each other, so they're free to move, so they're going to be further apart. So the potential energy refers to the relative position of the molecules. Okay, so when the molecules are further apart, the potential energy is going to be larger, which means that the amount of heat that you put in is going to go into the potential energy of the molecules. So the amount of heat required to cause a phase transition is known as latent heat. Latent means hidden. Okay, it's hidden in a sense that when you heat something up, you expect a temperature change. Temperature change does not happen. Instead, you end up getting a phase transition. That's what it means. All right, so the effect of it is hidden in a sense that you don't get a temperature change. That's the reason why it's called latent heat. So that's the amount of heat required to cause a temperature change for this amount. That's the amount of heat required to cause a phase transition for this amount of mass that you have. In essence, this is the amount of heat that goes in or comes out of the potential energy of the molecule during a phase transition. All right, so speaking of latent heat, the one that we will focus on is going to be water. So the water is the one that makes sense to look at. And instead of looking at numbers in terms of joules per kilogram, we're going to look at numbers in terms of the way we understand them. That's going to be in terms of calories per kilogram. All right, take a look at water. All right, so if you want to turn water into ice, this is the amount of heat that you need to remove from ice. If you want to turn ice into water, this is the amount of heat that you need to provide ice in order to turn it into water, 1 kilogram of ice. All right, so you need to put in 80 calories of heat into 1 kilogram of water in order to turn into 1 kilogram of ice in order to turn into water, in essence. So that's what it means. And take a look at the heat of vaporization. That's 540 calories, kilocalories, but I'm going to say calories per kilogram of water. All right, so here's what we're dealing with. If you want to take 1 kilogram of ice and turn it into water, you need to provide it with this amount of heat. So it's going to require 80 calories of heat in order to turn it into water. If you want to take water and turn it into ice, you need to remove this amount of heat from water in order to turn it into ice. If you want to turn water into steam, so you got 1 kilogram of water, so you need to put in 540 calories of heat into it in order to turn it into water. In order to turn water into steam. You got this amount of steam. If you remove 540 calories of heat from it, it's going to turn into water. Okay, so that's what it means. Okay, so far it's blah, blah, blah. So we're talking about some abstract concepts, but they're not that abstract. Remember the condo that I decided to buy roughly about 20 years ago? I decided to buy that condo right next to a lake on purpose because I go jogging at night, almost every single night. And when you're right next to a lake, when the lake starts to freeze up, guess what? It tends to be really, really, really warm around the lake. Why? Because you take water and you're trying to turn it into ice. So what do you have to do? You need to take this amount of heat from water in order to turn it into ice. So what happens? This is the amount of heat that needs to be extracted from water in order to turn it into ice. So this is the amount of heat that's released into the surrounding environment. So when it's really, really cold outside, obviously the lake starts to freeze at 32 degrees, except the surrounding area tends to be about 50 to 60 degrees because the amount of heat which is extracted from water gets released into the environment. And then it becomes really comfortable, so I can go jogging usually at night in my shorts until the lake is completely frozen. It makes life easier. So what I end up losing AC system, I end up gaining it by the fact that I was actually living by the it's worked out in that sense. All right, so things evened out in that sense. Let's put it that way. Okay, so this is problem number 3. It's an interesting enough problem. So what do we have? We got a lemonade at 27 degrees. It's inside a styrofoam cup. And then we got ice in lemonade. Okay, so what's happening is after ice and the lemonade reach a common temperature, the equilibrium temperature, it's interesting to know that there's still some ice remains inside. Okay, so, and then what we're trying to figure out is determine the mass of the ice that has melted. We're trying to figure out the mass of the ice that's melted. All right, so how do you solve a problem like this? Okay, so this seems like a really complicated problem, but it's not. Okay, so the first thing we need to do is we need to list everything that we got. So what do we have? So this is the amount of, okay, number one, you know that the common temperature is going to be 0 degrees or 0 degrees Celsius because we got ice. Some of the ice is melted, but we still have ice in water. So the only way the water, the lemonade, and the ice will coexist is if they're at the same temperature. So you know that the final temperature is 0 degree at this point. All right, so here's the mass of lemonade. And the temperature of lemonade is going to be this. All right, so here's the initial temperature, here's the final temperature. And that's as far as we will go. All right, so what else do we have? So we're trying to figure out the mass of the melted ice on that in terms of kilograms. So here's the specific capacity for water. It's going to be the same as the lemonade according to this problem. So if there's any ice remaining in lemonade, the final temperature is going to be 0 degrees. So we discussed that already, 0 degrees Celsius. Conservation of energy dictates that the amount of heat gained and the loss will be the same. So ice is the one that's going to gain the heat. The lemonade is going to lose the heat. Except, okay, so the math here is not tricky, but it requires a bit of understanding of what's going on. What's going to happen at 0 degrees, the ice is going to melt. All right? So the amount of heat gained by the ice is going to cause it to melt, so which means that it's going to undergo a transition. So this is the mass of the ice that gets melted. And then the heat is going to be lost by lemonade, in essence. All right, so all thing you have to do is just solve for M for ice, which happens to be this. And what looks like a really complicated problem resolves itself fairly fast. So the latent heat for ice is the same as water, so it's going to be expressed in terms of joules per kilogram. So you have to look that up. All right, so just to give you some reference points, lemonade was 80 degrees Fahrenheit. That's a hot lemonade. That's pretty odd. The 32 degrees, the freezing point for water. And then you plug the numbers in, you get a number in terms of kilograms, and then I express it in terms of pounds, so it's a fraction of a pound, so it's not a big deal. Okay, so we talked about conduction before. So it's going to be the bulk movement of the fluid. Usually it happens naturally because of change in density, or you may have to so there's nothing new there. Conduction is something that we dealt with before, so it's related to the transfer of heat through the collision of molecules. So what gets transferred is the kinetic energy of the molecule. So hotter it is, the faster they're moving, and the cooler they are, the slower they're moving. All right, so it's related to kinetic energy. We set up the formula before, so we will go through the same formula before we look at an application of it. All right, so it's the amount of energy transferred from molecule to molecule in the form of kinetic energy of the molecules. So it happens through collisions. The bigger the temperature difference is, the more heat is going to be transferred. The longer the length across the temperature gradient is, the smaller amount of heat is going to transfer. It depends on the exposed surface area, depends on the duration, time of duration, and it depends on the thermal conductivity of the material. And then at the end, we end up getting the formula, so it looks like that. So this is the formula that will give you. So we looked at the numbers. Bigger the numbers, the faster the heat gets transferred. Smaller the number is, slower the heat gets transferred. So styrofoam is not a very good conductor of heat in general. Fur is not a good, it's not a very good conductor of heat either. So if they'll keep it.
Are you ready, boys? Ready?
Some things we may never understand. Some things we should. At Reliastar.
All right, so bigger the temperature difference is, the faster.
We hear that mind over matter is an easy thing to accomplish. You just have to convince yourself that the bizarre thing you're doing isn't going to kill you.
It is your positive energy that will make this evening a success. Very important. We must have positive thoughts.
So how do you do that when you're staring at all this flesh-numbing hypothermia-creating ice water? Now, here are 6 supposedly advanced Taekwondo students in Ontario, Canada, who figured the best way to test their self-control would be to cut holes in the ice of a freezing lake and sit in the freezing water for a while. Like a half an hour, to be exact. And they claim that they didn't care if their hypothermic bodies began to shake uncontrollably, as they inevitably did, since these water temperatures could drop as low as 20 degrees. Now, they did make it out alive, which will probably give them the idea they can continue thumbing their noses at future medical warnings. Who knows? Maybe next time they'll try to sit in a fire for a half an hour. After all, it's just mind over matter.
Okay, so how were they able to maintain a steady core temperature? Body core temperature. All right, this is different from the cases that we've seen before. Notice that their bodies are partially immersed. Their cores are usually out of water. Being taller, I think, helps. Being thicker also helps, obviously. And a lot of it is in the training. Okay, so if you get it up to your neck, that's a completely different ballgame. Being taller helps because there's a larger distance between your core. Like this guy, it's almost above his belly. So obviously his core is somewhat protected. This guy is it's not as tall. And his core is very close to the water. So this is probably going to be more difficult for this guy. And having a nice little fat layer of fat also helps. But the rest of it is in the training, obviously. So that worked out pretty nicely. Okay, so this is problem number 5. I don't see the problem number 5, but this is from the handout. So the excessive heat is going to be transferred through the skin. And so while the body is trying to maintain a steady normal temperature at 37 degrees Celsius, that's what is 98.6 degree Fahrenheit. Okay, so the one possible mechanism for transfer is conduction through body fat. All right, so it's a made-up example from a book. So it says, suppose that heat travels through this amount of fat. So this is the thickness of the fat that it needs to go through. This is 3 centimeters. That's like a 1 inch of fat that you're looking at. And which has a total surface area of, this is a huge surface area, 1.7 square meters. And the temperature is going to be 34 degrees outside. Okay, so it's actually fairly warm outside. So find the amount of heat that reaches the skin in half hour. All right, so here's the inside temperature, here's the outside temperature. Okay, so here's the thickness of fat that it needs to go through. And assumption is that there's a uniform layer of fat which has this thickness across the exposed surface area, which happens to be that. So what is the amount of heat which is going to be lost by the body within half hour? What is the amount of heat that's going to go through fat within half hour, in essence? So that's what we're looking at. Okay, so I've done the conversions to seconds. That was the only one that required the barrel conversions. So the outside temperature is 93 degrees. That's actually pretty hot. All right, so it's almost an inch of fat under the skin. That's the layer of fat that we got. That's the thickness of it. All right, so the rest of it is just do the conversions and then plug the numbers in and then convert it to calories. All right, so that would be 15 calories of heat that gets transferred. All right, out of this, there's a problem that comes about. Okay, guys, this is one way of losing. If you want to lose weight, this is a good way to lose weight, except requires a lot of discipline. Okay, so notice that the temperature difference is fairly small. if you expose yourself to like cooler temperatures around 32 degrees or 28 degrees, if you can bear to sleep without losing consciousness, you will end up losing a lot more heat in the form of calories. All right, so the transfer of problem number 7. Do I want to do problem number 7? No. Okay, so problem number 7 is something I would focus on. I mentioned this before the test. Okay, I would focus on a problem like this. This is a standard test problem. I'll mention it during the recitation session for this one. All right, so the next one is the radiation. Okay, so the heat is going to be transferred in the form of electromagnetic waves. So the temperature of the source is important. In terms of this formula, I'm just trying to set up the basic radiation formula. Okay, so you take every single contributing factor and then string them together, and then multiply everything with a constant proportional to constant. That's the Stefan-Boltzmann constant. And that gives us the radiation heat formula, in essence. Gives us the basic formula. All right, so let's take a look at the application.
Places we could never go before, including extreme environments. When designing insulation for the International Space Station, scientists were confronted with a set of problems found nowhere on Earth.
We don't have the benefit of Earth's atmosphere when we're in orbit, and not having that benefit, we're exposed to much more extreme environments. In the same orbit, we can see temperatures in excess of 250 degrees Fahrenheit while we're in the sun, while a few minutes later be exposed to conditions that produce environments less than minus 250 degrees Fahrenheit. And we go through this 16 times a day, every day, 365 days a year.
Scientists had to rethink the entire insulation process when designing the station. The rules that govern air and heat movement on Earth simply don't apply in outer space. The Earth's atmosphere allows heat to be transferred by convection. But in space, there is no atmosphere. The vacuum of space allows only for radiant heat transfer, usually in the form of energy waves emanating from the sun. Earth's atmosphere prevents it from being overheated by these waves. But the space station, without such protection, is subject to the extreme temperatures brought on by solar radiation. The scientists had to come up with an insulation that would safeguard it. Their solution was a multi-layer insulation, or MLI.
MLI serves two purposes. The first is to reject or reflect a lot of the sun's energy, and the second is to entrap heat that's generated internally. And by doing this, we can moderate the extremes that we see on orbit.
Okay, so problem number 8. Let's just focus on this one. So Betelgeuse is a supergiant star, and we know that the surface temperature is about 29. It's going to be 2,900 Kelvin. So the question is, how do we know that? That's model physics. And this is the amount of power which is being radiated. All right, so it's got a temperature, surface temperature, which is about half of the sun, and the power generated is going to be 10,000 times that of our sun. And so we make the assumption that the Betelgeuse is a perfect emitter. So can we figure out the size from that information? Okay, so somehow if you can just measure the surface temperature, and then if you know the amount of power emitted, you can actually figure out the radius of it. Okay, so the question is though, how do we know what the surface temperature is? Okay, so that's from modern physics usually. All right, so this is the amount of power being emitted. This is the surface temperature. So can we figure out this radius? We assume that it's a perfect emitter. So all the heat which is being generated, 100% of it is being emitted. All right, so let's figure out this radius in terms of meters and miles. So here's the formula that we get to use. So this is the amount of heat which is being generated by the Betelgeuse. Okay, so temperature, okay, so that's fine. All right, so if that's the case, you can figure out its radius. So, okay, so back up a little bit. Okay, so here's the generic formula for it. Okay, so heat is energy. Energy per unit time is the power. So Q divided by T is going to give us the power. So that's the association that we need to make. The amount of energy transferred per unit time is going to be power. So energy is in the form of heat. E and Q are the same thing. So Q divided by T is going to be the power. So which means that we divide both sides by T. All right, so we got our power. Okay, so we know E, we know P. All right, so sigma here is the constant. We know the temperature in terms of Kelvin, so we can figure out the area. So we need to look up the formula for the area. Area of a sphere is going to be 4 pi r squared. So r is going to represent the radius. All right, so we'll do a back substitution. Isolate r from here. 4 pi's will cancel, e's will cancel, sigmas will cancel, so you have two cancellations. All right, so here's the final formula. Plug the numbers in after getting r all by itself, and that should give us the radius in terms of meters, and then convert it to miles. So it's going to be 190,000 miles. Okay, so that's how we do. That's one way of figuring out the size of these stars. Okay, from a practical perspective, though, there's something here that we're going to be looking at. There's going to be an interesting conclusion that's going to pop out of this example. Okay, so we got a wood burning stove. Okay, at the room temperature, that's 18 degrees Celsius. And then you start a fire inside the stove. Eventually, the temperature is going to rise up to 198 degrees Celsius. And then the room is going to warm up to 29 degrees. All right, so room temperature is going to be 29 degrees. Evidently, stove emits like 90% of the heat. So that's its emissivity. It's got a measured surface area. It's going to be 3.5 square meters. Okay, so the question is determine the net radiant power generated by the stove when it's unheated and when it's heated. Okay, so what's the net power, radiant power? So once again, here's the formula. We discussed how this formula turns into a power formula before. All right, so the amount of power depends on the temperature of the source. Okay, so I'm gonna do this the long way, not the wrong way, but the long way of doing it. All right, so if your source is the stove at 100 degrees, this is the amount of power it's going to emit. And if your source is the room, this is the amount of power that's going to be emitted or absorbed. So whatever the power which is emitted is going to be the same as, all right, so the amount of power emitted by the stove and the amount of power which is absorbed by the room is going to be the same. So the net power is going to be 0 because both of them are at the same temperature. Okay, or put differently, the amount of power which is going to be emitted, the net power is going to depend on the temperature difference between the hot and the cold regions, raised to the 5th power. Okay, so this is, I just took the formula that we had previously and I just generalized it. Okay, so there's something here that I need you guys to kind of understand, as the heat always flows from hot to cold. Okay, so if there's any temperature difference, there's always going to be a heat flow. All right, so if there's no temperature difference, there's no heat flow. That's known as the zeroth law, as we discussed before. So there's no power loss or gain under the circumstances. So this is the heat which is going to be emitted by the stove, and this is the power. This is the amount of power emitted by the stove in the form of heat, and this is the power emitted by the room at this temperature. If you're looking at the net heat, then you have to look at the power emitted by the stove and the power emitted by the room. So you're looking at the temperature, looking at the difference in power in essence. So instead of using it this way, we could use this formula, and we could do everything the same way, except now you're looking at the difference in temperature, which would have given us exactly the same answer. All right, so use this formula. Okay, so why is this important? This is important because heat is always going to flow from hot to cold. If you're wearing something dark, for example, they tend to be very good at absorbing heat. So which means that if it's hotter outside, your body's going to heat up faster. If it's cooler outside, your body's going to cool down faster.
If no one tries to get you, they'll die too. Honey, please. Please go back. Go back and help you lose to the surface.
I am not losing you.
I can't let you do it.
No.
I can't let you die. I'm sorry.
What are you doing?
I love you, honey.
No. No.
God, no, I love you.
Wait. Don't. Wait. Wait. Don't. No. No. Please, God, no. Honey.
All right, so this guy exposed himself to the full vacuum of space. The reason is they got separated. All right, so he's got no boosters or rockets. Under the circumstances, this is a law of inertia, so he's going to keep on moving in a straight line at a constant speed forever. All right, so there's no hope for him, so he decided to just get it over with. So he exposed himself to the full vacuum of space, and then that's it. Okay, I'm laughing because of the comments. And then notice that it's frozen immediately. All right, so is this realistic? Is this what happens in real life? The answer to that question is no. This is not at all what happens in real life. The reason why this is not what happens in real life is, guys, space is 3 Kelvin, so it's really, really cold. But your body is 310 Kelvin, so there's a huge temperature difference. But losing heat in the form of radiation takes a while. Okay, it's not like convection or conduction. Just about the only way you lose heat in space is through radiation, except it takes a long time for your body to freeze up. It's not going to happen within a fraction of a second. So it's not realistic. It's not realistic. So that's not at all